We're well on the way now to the final result, but still need a little bit more work before we get there. In this video, I need to take a detour into a subject called distributions. Again, this might seem like a strange detour, but it will all be part of the process of solving DEs with Laplace transforms. So what is a distribution? Well, it's something that is not a function, but is sort of like a function. It's an extension of the idea of a function. It doesn't have all the normal properties or even definition of a function, but it has one very important property. It can be integrated. Distributions are used throughout mathematics, but perhaps are most important in statistics, where probability distributions are a very main idea, and you may have heard of them in that context. In this context, I want to talk about one specific distribution, the so-called delta function. The word function is unfortunate here, since the delta function is certainly not a function. Nonetheless, the term delta function is conventional, so I will stick with it. What is this delta function? Well, the key thing about a distribution is that it can be integrated. The delta function at a real number a, and there's one for every real number, is written delta sub a, and is defined by these two integration properties. It's just a thing that does this when you integrate. The integral of the delta function over all real numbers is exactly 1, but the integral of the delta function at a times any other function is a valuation of that function, f of a. This actually makes the delta function literally the nicest thing in the world to integrate, because whenever you integrate it, you just evaluate anything else that is in the integral at the point of the delta function. This is very strange, but let me give you some context to understand what the delta function is like and where it comes from. So I'll start with a bell curve, and again, the parallel with distribution statistics is prominent in that idea. So here is the equation of a bell curve centered at t equals a. B is a measure of the spread, the standard deviation if you wish, of the bell curve. The coefficient here, root b over root pi, is put there to ensure that the area under this bell curve is exactly 1. And here is the integration to check that area if you want to verify it. As I adjust b, I can make this curve wider or narrower. If I make b large, the curve becomes taller and taller and narrower and narrower. And here's the diagram showing that process. The area under all of these curves is exactly 1, but the shape is different, becoming narrower and taller as b increases. So if as b increases, the curve gets narrower and narrower, what happens in the limit? This is a bit strange. I haven't really taken the limit of functions this way, but let me try it. Well, in the limit, the curve will become arbitrarily narrow and arbitrarily tall. And if a limit makes sense here, well, then that limit will no longer be a function, but it will still be some kind of thing. And it is a distribution. Specifically, it is the delta function. And sometimes the delta function has this odd definition. It's an infinitely tall spike at the point A, so the value at A is set to be infinity, and nothing else is left, so the value is 0 everywhere else. And importantly, the area under the curve at all points in that limit was 1, so the integral of the delta function will remain 1 in the limit. Now obviously infinity is not a value, it's not a number, this is not a function. It's a distribution. However, this is a good intuition for the delta function. Think of it as an infinitely tall and infinitely narrow spike at t equals a, but that the area under the curve, so to speak, of that spike is exactly 1. The delta function is not a function, but it can be integrated. Therefore, it has a Laplace transform. I can calculate that Laplace transform, and this calculation is surprisingly easy. The delta function, as I said, is the nicest thing in the world to integrate. It just picks out the value at a. So the result here depends on whether a is positive, 0, or negative. If a is negative, this integral is 0, the delta function transforms to 0. If a is 0, this integral evaluates to exactly 1, and if it's positive, this evaluates to exponential decay. So the Laplace transform of this not even a function distribution is actually a function, And it even gives the very normal constant function 1 in the S-domain, and then the very normal exponential decay. This is some evidence that the delta function is important to the theory, and the Laplace transforms work well with distributions, even more so than functions. This is also one of the few examples to the fact that the result has to be a decay. The transform of the delta function at 0 is constant 1, which is not a decay function. Again, almost everything in the S-domain will be a decay function, but there are these very odd circumstances where we get something else. Finally, before I end, let me talk about the interpretation of the delta function. Even though it is not a function, it actually shows up as a forcing term in a harmonic system. What on earth could this mean? Well, the delta function only happens at t equals a, so it is something instantaneous. It has a finite area, the integral of the area into the curve, so it represents some finite force. Putting these two together, the delta function represents a sudden impulse. It's a model for hitting something. A golf club and a golf ball, a bat and a baseball, a pendulum and a hammer, so forth and so on. Even though it isn't a function, it actually models something very concrete and useful. It models sudden impact. And you'll see this in the example where I use the delta function for precisely this purpose.